Hello and welcome everyone to Iron Beetle. Iron Beetle is a show about the Target database. And basically we just go and disassemble the database. We look at every single, well, not at every single line of code, but at most of lines of code of the database and try to understand how this thing works. And that's actually a very useful exercise to a large degree because the Target database is written in a particular database code style called target style, which in particular includes the clause that this database doesn't have dependencies. So by studying this piece of software, you understand how, you understand everything about the databases which is there to learn about the kernel. We don't so far go inside the Linux kernel. Oh, I think there was one episode where we did look a little bit inside, but I don't remember. But yeah, everything about the syscalls, everything about IO Uring, we study. And today we have a very special episode, an episode inspired by so-called letters from readers. So this week I've read this. This week I'm failing to share my screen. Okay. This week I've read this exciting, excellent blog post, an epic treatise on error models for systems programming language, and I highly recommend this post. And I especially recommend this list of prior art. So I mean, every link here is and now a gigantic text, which is well worth studying if you want to understand the topic of error handling. Today, very much directly inspired by this blog post and by our exchange on Lobsters with the author of this blog post, Type Sanitizer, most excellent nickname on the internet. I would like to discuss the topic of error handling in general, and in particular, the way we approach error handling in Target. Okay, so let me get into my philosophical hand-wavy mode here and try to set the stage. So, I mean, why do we need to talk about error handling at all? I mean, like, every language like solves this, like, there is like exceptions in Java, there is like question mark in Rust, there is like try in Zeek, there is like if error equals nil in Go. Like, I mean, every language has like mechanisms for doing error handling. And like, you see, like, we like every language has like slightly different way to do iteration. Like, there is like for loops, there is like while loops, there is like counter based for loops, there is like iterator based for loops, there is like internal iteration, there is like external iteration. But we don't spend an entire episode of Ironbiddle discussing how to write a for loop. From a language perspective, error handling and like loops look kind of similar. Yeah, there is like a common pattern of like iteration or error handling. And like, if you are Haskell, they're kind of like both monods, and there is like first-class support for like this part in various programming language. So it feels like, I mean, it shouldn't be a problem. And yet, I personally, as a like practitioner, as a systems programmer, find error handling like hellishly complicated in comparison to basically every other thing solved directly in the language. So to kind of like cut it short, I would say that I do not know how to, well, let me say, how to manage errors. Because even the title, error handling, is actually misleading. Because like most of the error management infrastructure, most of the error model is not actually about handling errors. So shout outs here to Joe Duffy, who suggested the error model terminology, and to our very own Without Boats from Rust, who suggested the term of error management and emphasized that the error handling is only a small part of error management. So yeah, you see, I mean, like such luminaries, and like we can also add like Joe Armstrong into like this list, thought hard about like the error management problem, and I sort of feel that the problem isn't really solved yet, both like in theory and as practice. So yeah, that's kind of like my overall thrust here. Like I'm mostly confused. I'm not hopelessly confused. Looking at various projects, trying different things, reading a whole bunch of blog posts, I think I have a mental model inside my head of like how to do error management. Like, if I have a task of like writing some kind of an application, I will be able to think hard a little bit for a while about it, then look at a particular programming language I will be using for this application and come up with a strategy which I think would be okay for this particular application for how to manage error. The problem is this will require like, very active thinking from my part. Again, the iteration analogy. If I need to like, write some kind of an application, I wouldn't have to think about how to write for loops. I would just go and write like, for, or if it's like functional language, I will write map or reduce and be done. Like, there's like zero thinking. It's like very well understood. For error management, yes, I would have to really think about what I need to do in this particular case. And what infuriates me is that I don't think there is a concise way to kind of like, compress this into a single paragraph of text and put it in your style guide and like teach everyone like, hey, this is how we do error handling here. No, it is every single time it is like, there is specific case, hey, we are looking at this particular error and this is how we deal with it, and with this other error we deal in another way, and it's like hugely complicated. Okay, so that was giant preamble. Let's start on the topic of error management in particular. And here again, I want to highlight this blog post because it verbalizes and names one crucial aspect of error management, and that is the word context. This is it. Where a program state is an error or not is contextual. Let me explain the way I read it. The way I read it is that there is no universal error management strategy. An error management strategy is specific to an application. So if you are writing an IDE, your error management strategy is like one thing. If you are writing an HTTP web server, your error management strategy is a different thing. If you are writing a database, your error management strategy is the third thing entirely. And that kind of like makes sense. There's like two problems here. One is that because different applications need different error management strategies, it is hard to compress this knowledge into a set of simple rule of thumbs which you can thoughtlessly follow. You need to think like hard, like, hey, what is the context I am in, and what is the appropriate way for me to react to errors? The second thing is that I very deliberately phrased this as application-specific context. Dependent on an application, you do this or that or something else entirely. What if you're writing a library? Well, I mean, this is hell. I don't know how to do error handling in libraries. It is always like hugely complicated because in libraries you actually don't have access to the context, and you cannot like apply rules from that context in your library. And kind of like to just like give like a very simple example of like why it is hard to do error handling in library. Let's say your library has, I don't know, some config file parsing or something like that. And let's say there is like a horror integers in that context. And you need to parse integers. And obviously you need to emit errors, like, if integer failed to parse. And I mean, imagine that integer is like unparsable is not super hard. Like, you say, hey, like parse int error and like something. But then what if the application into which you integrate your library needs localization? Well, probably it actually needs localization. Like, I mean, everything outside of systems programming generally is, and many things inside systems programming are aimed at people for whom like English is not native language, like myself. So there's a need of localization. And how do you localize the error message? I mean, if you include some kind of like string description of your error message for parsing error, and it's like not localizable immediately because strings are hard to localize. But then, okay, you need to like expose like, hey, I like expected to see like a digit here and I saw something else. But that actually exposes the details of your parsing algorithm. And if you think about it, if you are going to present this error message to the user, you might actually want to use a different parsing algorithm in your library just so that you could do, just so that you can produce a better error message. A parsing algorithm which is aimed not at simplicity and not at performance, but at being helpful to the user. And that's kind of like what makes life of library offers help. Luckily, I am bad at writing open source libraries. I like hate maintaining them and hate maintaining public APIs. I like throughout of my professional career, I worked mostly on applications, on IntelliJ Rust, on Rust Analyzer, on Stepik.org, on Rosalind.info, and now at Target. So my experience is mostly in managing errors in the context of application, where the context is fixed, different in different applications, but fixed. And this is what I'm going to talk about, like how to do error management in the context of a particular application called Target. Okay, so before we start, let me maybe. Well, okay, no. Let's just start. Okay. And I haven't prepared super strongly for this episode, so we'll kind of like, as usual, we'll be like discovering things as we go. Again, if I had more time, I would have written a blog post, but I don't have time, so I just go live on Twitch and say what comes to mind. Okay, so as a simple exercise, as a simple example, let's look at how we deal with like the simplest possible error that can happen if you use the database wrong, and that is if you pass some kind of a wrong CLI argument. So let's wait until it okay. So okay, let's say that we want to format and we parse XYZ as cluster ID. So that is obviously an error, and something should happen here. Actually, and now I'm a bit nervous because I've never actually in the real life passed a wrong number as a cluster. So if like, you know, there's going to be like some nasal demons right now, well. I would not expect this, but I also wouldn't roll this out. Okay, so let's wait while Andrew works on faster backend for Zik. Okay, yeah. Okay, actually, this is slightly less helpful because it is not clear which is an error from the Zik build system, which is an error from our program proper. Let's run it directly. So yeah, you know, error happened. We print a message and we exit with status 1. Pretty reasonable behavior. How is this realized? Let's see. So we go in the CLI.zik. And this is our like CLI arguments. And this is like the cluster for the format. And you see that here it is already integer. So yeah, once we get here, cluster, so this thing will already be an integer. And that means that error handling is, in this particular case, is actually in the middle of our flags parsing library. So let's see, and there should be, okay, yeah. So I'm kind of like skipping through a lot of code here, but eventually we'll go into parse value int function, where we will invoke standard library to parse an integer, and that returns an error. So we catch an error, we exhaustively match on it, and then we call the fatal function. And the fatal function does something pretty horrible, actually. I mean, you usually don't write this code, it's fatal libraries. So it goes and it prints directly to standard error. It kind of like doesn't try to figure out what what the user wants to do with this error, and just prints it. And then, like, what's worse, it goes and immediately aborts the process. And here is the first lesson of error handling which I've learned, is that in the context of applications, you really should think about how your error is going to be used at the end. Because, I mean, like, you know, how you type your errors, how you propagate it. Do you write try? Do you write question mark? Is a propagation explicit? Is a propagation implicit? Is a propagation through like stack unwinding or like through like return types? It doesn't matter in the slightest. What actually matters is what you are going to do at the very end. how error is eventually handled. And here we are deliberately using this word handled. And the thing is, when you are writing a library, you don't actually know how the error will be handled because you don't know who will be calling your library. The set of callers of your library is open. In the case of an application, it is closed world. You know what is the end destination of the error. And in this case, I've found it hugely useful to not propagate the error and instead to just immediately do what the error handler would have done otherwise. So for CLI argument parsing, again, I'm writing an application, so I know that this will bottom out in me printing some kind of a message and exiting the process. And I can implement this by formatting my message at the point where it originates into some kind of an in-memory buffer, and then propagating my memory buffer upwards through the call stack to the main function. And then in the main function doing like this print and exit dance. But I kind of like, and honestly, like a lot of time, like I did this. I used to do this a lot. And then I kind of like realized that actually, I mean, this does not buy me anything. I mean, I already know that I'm going to print and I'm going to exit the process. So why don't I just print and exit the process immediately and simplify the whole thing? So this is, I think, like my rule of thumb for application development, that at the point where in your application, where you know how the error will be handled eventually, you should just invoke the handler right there on the spot. You shouldn't propagate the error upwards. And there's like two reasons for that. One reason is just simplicity. I mean, here, like you see, like we just like a very direct simplicity in that although we print an error message, we don't have to allocate it, and we don't have to store the data for printing error messages. We just do it here. The second reason is actually related, and that reason is that you actually have most of the context at the point where error occurs. When you start unwinding the stack, when you start popping frames from the stack, this is where you erase the context. This is where you lose access to your local variables, to your local state. Here, at the point where actually where the error is emitted, it is like you have the fullest view of the world. And here you can actually go and take advantage of that fully to print a nice message. Okay, so that is the one. That is one pattern. In the case of Cyber, and I mean, again, this pattern doesn't mean that whenever you see an error, you immediately crash. No, that is not what I'm saying. What I'm saying is that if you know what is going to be the end result, you should just go and do this end result immediately. Another great case for this is if you are writing an HTTP web server, such that like a web server which works on request-response basis. There, for every error, you actually know what is going to be the end result of an error. The end result of an error is going to be an HTTP response with a status code of either 400 or 500 and something how do you say it properly, 400 something. And then maybe a JSON payload, maybe an HTML payload, which explains what is an error. And if I were writing a web server, this is how my error handling strategy would look like. I would say that the error, like the error type in my application is actually an HTTP response. And whenever I would have emitted an error otherwise, I would immediately convert it into that HTTP response and like quote quote throw the HTTP response upward. I would have to do some form of like unwinding, either like stack unwinding or just like returning the value. But what I would be propagating upwards would not be some like error type. No, it would be a normal HTTP response. Okay. So this is okay. The first rule of thumb. Whenever you know how the error will be eventually handled, just go and handle it right there in that way on the spot. Okay. The next error handling pattern, and this is it is mostly associated with databases, but I think it is a generally useful pattern. Like, okay, so let's say we are running some long-running application in terminal. Like, yes, like the way we stop this application is that we send a signal to the application in at least Unix. We say like Control-C, which kind of like pogs the application and say, hey, could you please stop? And at that point, the application actually has an option to say, hey, yeah, let me like, save some files, send some message over the network, and then I will stop. So usually this is done by installing a signal handler for SIGINT. And we can see how TigerBeetle deals with signal handlers. So we see, yes, we do have some signal handling logic in main, but this is actually fun. This is fun, unrelated but fun. What this, kind of like, to cut it short, this is not a handler for SIGINT. There is no handler for SIGINT in TigerBeetle database, and I will explain why. But first, I would like to explain like what we are doing here. So one problem with TigerBeetle is that we need like relatively modern CPU instructions for our checksums. And maybe for some other things, I'm not sure, but for checksums for sure. And yeah, sometimes people try to run our code on CPUs which do not support those things. And I mean, you would think that people don't actually run on all CPUs these days, and it's like completely an edge case, but it's actually not an edge case because there's like one case where this is pretty frequent, and that is if you run an x86 program on ARM Mac through Rosetta. So Rosetta doesn't implement some of like fancier cryptography instructions, and it crashes pretty badly with an illegal instruction. So we want to provide a nice error message here. So we kind of like catch a signal we get from an instruction and say, hey, TigerBeetle releases are compiled with modern CPUs, blah, 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 blah. So that's why we do it. The fun thing is, the fun thing here is that this code in general doesn't work. You cannot emit a nice error message on an unsupported CPU architecture, because if the CPU architecture is unsupported, you're likely to hit SIG-EAL before you get to this message. So in particular, I think on some older CPUs, we actually get like a second SIG-EAL while we are trying to print stuff. Well, at least we tried. Okay, so this brings me back to the absence of SIGINT and to another pattern for handling errors, which is associated with the databases, but which I think should be part of more or less every application. And that pattern is called crash-only software. So one of the possible error cases for your application is that your application gets killed abruptly in the middle of the thing. Like, your application was like computing things, like maybe reading files, writing files, talking with someone over the internet, and then bam, I don't know, greedy handler or killer, or maybe, I don't know, just sloppy user with like Control-C, or some I don't know, antivirus, or maybe like virus program just decides to kill you, kill your process. And this is totally a possibility. Processes can be terminated abruptly, and we need to deal with it somehow. And an incorrect way to deal with possibility is to try to minimize the extent of abrupt crash. Try to kind of register all kind of signal handlers, add nice exit button to your web application, maybe do something else, but this is not solving the problem fully. There are going to be cases where your program will be killed abruptly. So a better way to engineer this is to say that, hey, I just accept that the process might be terminated abruptly. And I will make sure that no matter whether my process terminated normally or abnormally, the data is going to be safe. And actually, I will go further. I will just not implement any kind of normal way to shut down my process. There is no signal handlers, no escape key, no exit button. Just crash the process, just kill it. That's normal. Well, how do you do it? In terms of normal application, that basically means that you should store your data inside a database, and you should wrap data transformations into transactions, such that every specific transaction either passes or fails. And it is up to the database to decide which is which. So if you work with persistent state in a transactional manner, then you are naturally immune to getting abruptly killed. The question arises, okay, what if you are a database? As a database, how do you ensure that you are immune to abrupt process termination? Well, the way we do this in Tagabital is through this superblock quorums struct pattern. So as a reminder, the state on disk in Tagabital is append only. It is essentially a persistent functional data structure with a lot of pointers from grid blocks to other grid blocks. The root pointer is stored in the so-called superblock. Superblock is stored on disk as 4 copies. And to advance the root pointer, Tagabital overrides all the 4 copies, but it overrides them one by one. So the worst case that happens is that you overwrote your first copy, you crashed halfway through overwriting the second copy. So the second copy is completely invalid. Part of the second copy is the old data, part of the second copy is the new data. And the remainder 2 copies are the new copies. Okay. So this can happen, but if you start up, you will start with, you still can read the old copy of a superblock. So your data is still there. Okay, So that is the second pattern for error handling. Kind of like the topmost handler is a operating system, which can just kill your process abruptly, and your goal is not to handle this error, but to manage it, to make sure that no matter whatever termination happens, your data is going to be safe and sound. Okay, so let's look at some other patterns for handling errors. So most of the errors, like almost exclusively all errors actually, come through input-output. You read something from disk, you try to send HTTP request, you do some IPC through pipes, or you try to spawn a process and there is no such process in your path. This is where like error happens. So let's look at input-output. For example, let's look at our favorite message bus. So message bus, you know, is responsible for networking. And let's see what happens if we get an error while we send a message. How do we handle it? Okay. So here's our bus. And this is how we say, okay, please, dear bus, send this buffer to this socket. And when the separation is done, we invoke the callback. And the callback is a result. It is either the number of bytes actually sent over the network, or it is an error value and error code. And here, you see that the error handling is super simple. So when we get an error, we print it, and then we terminate the connection, and with it, and we return. And I mean, we return here. We don't unwind the stack. We don't try to communicate this kind of error further. So when we terminate the connection, well, we just close it, and then on periodically. We'll actually try to see if there is someone we should be connected to and we are not connected. And then we will go and connect to the replica. So this is a very powerful error management strategy for distributed applications. In a distributed application, in general, you don't know whether particular operation succeeds or not. Because, I mean, even if you did send this message over the network, like the message, the actual packet with bytes of the message could get eaten en route by like angry pigeons or something like that. Like there's no like guaranteed delivery. So like there's always a possibility that things do not happen for one reason or another. And if that happens, the way you do, the way you handle this problem in the distributed system, you do a retry. So whenever you are doing, there is always going to be a retry loop somewhere. And that means that whenever you receive an error, you may actually just drop it on the floor, like log it and say, okay, so like nothing happened, we can continue. And again, this is like, you see, this is like hugely context dependent, again, because what we are doing here is this essentially like, you know, what they taught you to never ever do in your like Java classes at the university. Like you should never ever have an empty catch. Like, you know, if you catch an error, you shouldn't just swallow it, you should do something. But in the context of distributed system, well, actually that's what you do. You swallow the error and you rely on a retry happening like somewhere. And again, so there's like actually several retries here. So one retry is to reconnect to the connection, to recreate TCP connection. But, you know, ultimately, we also need to resend the message which we are going to send. So there is in the replica, there is this send message to replica function, which takes a message and sends it to replica, and it doesn't return any error and doesn't inform the caller whether the message was actually sent or not. Because in a distributed system, it's actually impossible to know whether the message was delivered or not. And it's not a problem, because there is going to be a retry loop to repeatedly send the messages until you are sure that the message is no longer needed. Okay, so that is the second pattern. And that is just especially in the distributed systems in my networking, just retry, and that's it. I guess while we are at it, we can take a look. Okay, yeah, let's drop a little bit down and see how the error message works on our interface with operating system. Because here actually we kind of there's a very good mapping between the errors which you receive from the operating system and the linguistic abstractions that Zeek provides you for managing errors. So okay, when we enqueue the send function, the send syscall into IOU ring, we pass in the callback. And let's see how this send error eventually materializes. Okay. So we have this definition of send error, like what could happen. And then when we receive a completion for our asynchronous syscall through IO ring, we just carefully match on all the error codes which man page mentions, and converts them to our well-typed error code. And some error code, we know that they cannot statically happen for our socket types. So we specifically do unreachable there, so that if we are wrong about this, then we kind of crash loudly. And finally, there is a special case for unexpected error. We receive an error code, but the error code wasn't mentioned in the man page, or maybe we were reading the man page incorrectly. So we want to understand whether we need to do something special to handle this code. So that's why we log it and print the stack trace. But that's actually it. Okay, so what is the moral of the story here? Well, the moral of the story here is that Zeek zero handling is exceptionally good for exactly this kind of thing, for receiving an integer from a syscall and converting this integer to a closed set of what actually might be happening here. At the same time, I would say that maybe this is a useless work right now, because you see, we don't handle anything here, and in the message bus again, we just log a message, and we never ever match on this error. So maybe actually we shouldn't do the work of trying to exhaustively match all the error codes there, because we statically know that the error is possible there. Okay. You might notice this, or you might miss it, but there was actually one very powerful, extremely powerful error management pattern we've seen in the code which was on the screen just a minute ago. So let's see again. Okay, so send function. This send function makes a syscall, and this is asynchronous syscall. And asynchronous syscall requires allocation of resources, because I mean, like, you know, ultimately, like this buffer here, this socket here, like this is bytes of memory, and this memory needs to be stored somewhere. And in general, like you need to allocate this memory, and you need to free this memory. And allocation can fail. So in a normal system, you would expect to have some sort of an error condition here for like, hey, I tried to allocate a resource and I failed. So I report to you that I cannot execute this syscall because I do not have the resources. You see that this is not the case for target. This function returns void. There is no like immediate error. Like, I mean, there is an error like here when you actually finish executing this thing, but that is different. That is an error for like the actual send work. It is not an error for like, hey, I do not have the resources to schedule your work. So how this works? Well, and the trick is there. We pass in completion parameter. So completion is some memory owned by the core, and it is passed as an argument. And the state we want to preserve during our asynchronous operation, this socket and this buffer, we actually store these like inside completion as a field. And then this completion, well, if we are lucky, we kind of like immediately copy it into the mmap for IO ring. But if we are unlucky, we just enqueue it into doubly linked lists of completions. So you see what we've done there. For our function to work, it needs some resources, and resource allocation might fail. And this is an error condition. But we remove this error condition by punting on resource allocation to the caller. So the caller should allocate resources somewhere outside of the hot loop of calling this function. And that way, we just completely dissolve this error. Again, this is super powerful pattern. And whenever you're working on an application, you should find a way to do this. You should find a way to completely excise errors from your APIs. You should seek ways to make your the core of your system infallible. Another example here is from Rust Analyzer. So Rust Analyzer is very deliberately, I mean, Rust Analyzer, at the end of the day, it needs to read the files, right? Like, you know, it needs to like go there to these kind of like read those like millions of like lines of like Rust code. And reading a file from this can return an error. I mean, probably it won't. I mean, I don't think I've ever in my programming career on my like, you know, laptop actually seen an error from reading from local disk because I don't like, you know, manually observe every single disk read, but actually like errors are very much a possibility. But still, you know, it's kind of like not a real problem, especially for like something like an IDE which can just crash. But still, like, you know, this can happen everywhere. And if you like, you know, wrap it properly in a result or like in anyhow or this error and like start propagating, that means that basically every single line in Rust Analyzer would have to account for a possibility of input-output error when, like, you know, eventually the data needs to be read from disk. And that is not how it works in Rust Analyzer. The core of Rust Analyzer, like the actual compiler work, is completely IO oblivious. It doesn't do input-output, and there's no error handling here. So the function which actually reads the data, the way it works is that, like, okay, if it read the data, okay, it returns the data. If it got an error, it returns an empty string, as if there is no error. And then, like, marks that, hey, we actually had an IO error here in some, like, out-of-bands information. So the core of the compiler doesn't have to account for the possibility of error at all. It is if the file system and the operating system are infallible. But the code which actually interacts with the user, there is this if which says, hey, actually, you see, while we were trying to analyze your project, we got an IO error when reading this file over here. So let's somehow inform the user that, hey, there is a problem there. So again, the second super powerful pattern, just remove the errors. Just don't do them. Okay, so let's see another interesting case when we read data from disk. Okay, so read sectors. We say, hey, we want to read from this offset, from this zone on disk into this buffer. And again, like you see, kind of like it's surprising that the callback doesn't have any possibility of an error here. Like, we just pass it a read. We don't pass it like, bank a read or something like that. Okay, so let's see that we start read. And then we do this asynchronous read call again. The same thing here. Submitting a syscall is infallible. And then we do a call when we get a callback. Okay, the callback is the callback does give us a possibility of error. So if we again see read error, you see there is like the same thing here. Well, and by the way, this is actually, again, you see, actually, I didn't realize that this is here, but this is interesting. So apparently, some file systems might fail to complete your syscall and just tell to you, hey, please do a syscall again, which is again pattern actually from distributed systems that, like, sometimes things do not work out, and then you should do retry. So yeah, no problem. We do a retry here, and this is again, like, it's important to, like, be able to exhaustively match on what is the error here, which is hard to do because this is like the operating system, like quote C API, which doesn't have exhaustive enums. So the way you write this switch exhaustively is by carefully line by line verifying the man pages, and then immediately verifying the man pages with, like, operating system you have in question. But anyway, otherwise it is just, yeah, like we map to exhaustive set of errors. So if you see read error, this is now like a closed set. So we know that these errors cannot happen and others cannot. Okay, so let's see. And here we actually see, like, there is like some actual error handling here. And again, okay, this is actually fully incorrect. Okay, again, so there might be like some, like, really Okay, no, actually no. So these errors, we know that they cannot happen from the way we use our system. Like, for example, we cannot get is directory because we know when opening the corresponding file descriptor, that the file descriptor actually is not a directory, it is a file or a disk device. So here we say, okay, just like, just crash the process entirely, which is very good. Okay, but this input output is interesting actually. Read error is, where are we? Yeah, okay, so this is like this input out. So this is only a single error code which leads to input output, and this is like a genuine error, like some hardware shenanigans happened. Our hard drive isn't well, like it wasn't able to complete our request. Okay, so the fun thing here is that the first thing we do is that we actually try to retry the offended syscall by shortening the buffer which we are reading. So kind of like, if we okay, I'm not sure. So like, okay, so if this is a transit error, we just solve it by retrying. If this was an error in one sector, then we at least get data from all the other sectors. So for example, if we are reading prepare and the body of the prepare is corrupted, we can at least get a valid header out of it. Okay, but that is if we can subdivide, if the size of our read is larger than our sector. Otherwise, if we cannot subdivide further, what we do is that we set our buffer to 0. And then, after we set our buffer from 0, we somewhere it should be, where are we invoking the callback? Callback read.callback. Okay, yeah. So like we zero out the part we were trying to read which failed. And then we kind of like say, okay, let's read the rest, and if there is no the rest, we return the callback. So this is again unusual, because we had an error, and instead of returning the error to our client, like as an error code, we just set the data to 0 and say, hey, actually your data was 0. And you would think that this is like problematic. So we essentially are swallowing errors, and we are lying to our caller that, hey, the data should be 0. But then again, context matters. We are inside of a database, and we are inside of a database which assumes that the disk might fail. So in addition to disk cleanly returning an IO error, we need to account for a possibility that disk silently returns wrong data. And that is possible, like pretty unlikely, but over long periods of times on a large number of hard drives, that totally happens. And we need to like somehow deal with it. So the way we deal with it is in the grid. Whenever we read the block, we then go and verify its checksum. And if the checksum is incorrect, we say, hey, your block has an incorrect checksum. So you see, like there is already an error handling path for invalid data and we turn error handling path for any other error into an error handling path for invalid data. So again, this is also like super powerful error handling pattern. Instead of just like, growing your atom with more and more options, actually try to collapse them. Try to say that, hey, there is just single error condition, something went wrong, and then you go and fix this particular error condition. Okay, so that's that is how we read great data from this and how we deal with errors. Okay, there is higher level thing which says I want to read grid block. So not an individual sector from disk, but actually like grid block with a particular address, with a particular checksum, blah 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 blah. So the fact in here is that the main callback we pass here, so like we are ignoring like from local storage, which we use. Let's for now just ignore local storage. So like the normal part for reading block is this. You pass this callback, and again, this callback doesn't return and doesn't allow for an error in the interface. There is no like, hey, either you got a block or you got an error. You always get a block. How that works internally? Well, that internally relies on the system being a distributed, replicated database, such that every block exists in at least 3 copies in the system. So the way this works, if a replica tries to read block from disk, and the block is corrupted, the checksum doesn't match, the replica transparently repairs this block from one of the 5 peers in the cluster. And the caller of this code doesn't have to deal with error at all. They always just receive their block eventually. And if it takes a long time to get the block, well, they just sit there blocked on a corresponding syscall. Okay, so that is again kind of like the pattern where you like dissolve an error by just going and transparently repairing it. Again, this is also context specific, very database specific, but kind of like my hunch is that if you're writing any kind of a large application, this is what you should do. Like you should figure out how to simplify error handling for you. Okay, so there's probably more I can be talking about, like how do we actually do error handling, but I think that covers the bulk of it. So let's recap. Let me turn my hand-waving philosophical mode again. Okay, so biggest thing about error handling. Error handling is always contextual. And if you are writing an application, this is a blessing because you know what your context is. If you are writing a library, it is a curse because I have no idea, like, you have no idea what the context is. And I don't have good advice for like library authors. I mean, okay, I have some advice for library authors, but that's going to be like, like 4 hours of hand waving more. So let's focus on applications here. Okay, for applications. This is, I think, like the golden rule of thumb, which does not necessarily help you to simplify the error handling, but certainly helps you think better about error handling strategies in your application. And this is the rule. Whenever in your error propagation chain, you know how the error will be handled at the end of the chain, you shouldn't propagate the error further, and you should handle it immediately at that point in time. So do not propagate the error needlessly. If you know that your application is going to exit and print a message, then exit and print a message right there. If you know that your application is going to crash, then crash write error. If you know that your application is going to retry, then like drop the message on the floor, drop the error on the floor, and do a retry right there. Okay, then the big pattern for error handling in applications is to take advantage of your domain and to remove exceptionalness from exception handling, to kind of like make errors normal. And to that end, I think we've covered several patterns. One is crash only software. So do not have separate quasi-error handling cancellation paths for your application getting teared down normally. No, always be prepared for your application getting killed abruptly, and just don't do any shutdown code. Second, in a distributed system, you do need end-to-end retries. And if you need end-to-end retries, anyway, that means that any intermediate error can be swallowed, because, well, there's going to be a retry. Then you could try to turn operational error into data errors, like in our grid block example, where we transform an IO error into a missing checksum. If you check data validity and you have handlers for invalid data, those same handlers you could use for operational errors if you treat an operational error as just an instance of invalid data. And yeah, finally, if you kind of like counterintuitively, if you assume that more errors can happen, then your error handling might become easier, as was the case with disk. Because TigerBettle assumes that the disk is failable, TigerBettle needs to include some code for repair. But that code for repair simplifies the error handling, because now the calling code can assume that the disk actually is unfailable and always returns valid data, because the underlying code takes care to transparently repair everything. Okay, so okay, dear, I mean, I really wanted to tell everything I know about error handling, and I feel like covered maybe like, I don't know, 10%. Which is kind of like underscores what we've started with. It's like error handling, error management, error models, sadly, is a vast topic. And there isn't, like, you know, quick and dirty, like, you know, 30 seconds short video clip which just explains how to do like error handling. Sadly, yeah, sadly you have to think, sadly you need to take a look at your specific context and figure out what is best in every particular situation. Or at least this is the best item. But still, I hope this is helpful. And please join us in a week at 5 p.m. UTC live on Twitch, and be mindful of daylight savings time. I mean, the time is the same for us, like 5 p.m. UTC, but it might change for your place depending on time zones. Anyway, next week I think we'll get back to actual plowing through all the database code. Okay. See you, and please handle your errors, manage your errors responsibly.